Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Yeah, so the first hello wasn't actually coming through, I think.
Oh, really?
I didn't unmute us. But now we are coming to you live on the internet tubes.
Hello, everybody. How are you all doing?
I'm in a mood today.
we're all in a great mood today.
I'm in a weird, goofy mood. This should be
You're always in like a goofy mood.
I was last week too. I was in a very odd mood. I'm feeling like I just want to make stupid jokes all day. I guess that's every day too.
Yeah.
That's not any different.
You should, if you're a YouTube member and you can join us on the stream, you'll get to see some like behind the scenes stuff where we're just like super goofy, like before and after the live stream and all that stuff. So yeah. Well, welcome to Ask Us Anything About Electrochemistry. I'm Dr. Alex Peroff. This is Dr. Neil Spinner. And we get a lot of questions from you guys, either from the phone, through email, webinars, YouTube comments. We get tons of questions. And so we have created this live stream opportunity where we can really go into depth into some of these questions and try to answer any electrochemistry questions that you may have. Now, we are using Restream as the platform, the encoding platform to broadcast this onto YouTube. And we've noticed there's maybe like a 20-second delay at most between what you type and what we say. So just keep that in mind during the live stream. This live stream is it's live, but if you're watching this after the live stream, we will have a description of all the questions in the description section of the video afterwards. So you can always find your question or any questions you may have missed after the live stream, maybe a couple of days afterwards. This is a space where you can ask any type of electrochemistry question. There are no stupid questions. Electrochemistry is extremely confusing and complicated. And I was just actually at an electrochemistry workshop last week, and I know a lot of people got really confused from that workshop.
After the workshop.
After the workshop, they had questions going in, and now they have more coming out.
Yes. Actually, that's kind of like, isn't that the mark of a good like PhD program, or just, I don't know, in some sense, like the more you know, the more you realize you don't know anything.
Yes.
You know, so like hopefully, I mean, if Alex and I can do anything for you today, it's to leave you more scared and confused than when you came here.
Yeah.
That's our goal.
Yes. We're going to apologize ahead of time if we mispronounce anybody's name when you write some question in the chat. We'll try to answer them. Also, if you are a tier 1 or tier 2 YouTube member, I posted a comment in as a tier 1 and tier 2 members that they can join us on Restream and actually ask the questions, like using your voice, not just typing it, but using your voice, and you have the option to even share your screen to discuss any electrochemistry questions that you may have. And actually today we have a guest who showed up. His name is Carlos. And so in about a minute, we will introduce Carlos with his question, and we will let Carlos introduce himself. I think I covered all the boilerplate stuff before we get into anything. All right, so now we are going to add Carlos onto the live stream. So Carlos, if you have a question, I think you should be able to chat or say something or share your screen, please try to say something if you can.
Hi, can you hear me now?
Yeah, we can
Yes.
hear you.
Let's see
Yeah,
if we can get you on the screen.
Yeah, well, there's no videos. Your
Oh.
video, yes, it's probably loading. It takes a second.
It might take a second.
I don't think it will load my screen, maybe.
Either video or your screen, either way.
That's fine.
But if it doesn't, that's okay. You can just talk and we can just hear you at the very least. So.
Yeah.
That's great. Thank you very much for hosting this session.
Yeah, thanks for joining.
I've been watching your videos ever since I joined electrochemistry. So I'm new to this field, and I feel like I learned a lot by watching all your videos. I'm mostly interested in EIS because that's like my main work that I do. So I usually work with lithium-ion batteries, and for me to understand the diffusion of the ions, I need to understand more the process. So I need suggestions to see what are some, based on your experience, what determines the diffusion of lithium ions in any batteries? Like,
So you're asking what? Well, there's two. I guess there's two ways to answer this, or I don't know, think through this. So the first is a more literal answer to your question, which is what determines the diffusion or what causes it, and the other is how to measure it. Are you interested in both?
I know how to measure by using EIS, using the Warburg impedance, or you can use a CPE.
Yeah.
But based on the literature, they always show very fast diffusion. But sometimes, how do you determine that? Like, how to fix that issue to get better diffusion?
Well, the first answer I'd give is strong concentration of electrolyte. You're automatically dealing with an uphill battle, let's just say, because the electrolyte in a lithium-ion battery is usually carbonate, salts, and things like that, which are not as favorable in that arena as compared to ATS, which you can't use obviously for lithium-ion batteries. So your diffusion is less favored or whatever. It's a little more viscous and things like that. But this is why typically people use like 1 molar LiPF6, right? You use a really strong concentration. So the more concentration of lithium salt you have in your battery, the less the effect of diffusion you will probably encounter, because you're not waiting for lithium to make its way anywhere. It's so saturated. Now, the other is that most batteries, you do not have, it's a liquid system, but there isn't a lot of liquid, right? You typically saturate the separator or the membrane with the electrolyte, but it's not really a liquid system. And so one of the reasons I think that people tend to consider the diffusion to be fast is because of that. It's not a flooded 3-electrode system where you're waiting for something to migrate, you're waiting for diffusion between reference and working or working encounter, anode cathode, whatever. You're not really waiting for a lot of that because it's a cell, it's pressure, it's close together, and it's physically very close. There's just not a lot of actual physical space between the anode and the cathode, which is good. So that means you don't have to wait forever for something to diffuse. And then the other is that, frankly, lithium is small, right? Lithium ions are very small. Lithium is element number 3. So even solvated lithium is really small. It means it diffuses fast. Just diffusion is a random walk. You've talked about that before, right? In various questions in the past. It's a matter of a lot of whatever, I guess, the solvation radius and things of that nature, right? What have you? But the size matters too. It's much smaller. Just like smaller gases elute faster. So similar sort of phenomenon with lithium ions. But and then the other factors, it's like the solvent, right? So I talked about it briefly, but like some people use ionic liquids, and ionic liquids are great because they have 0 vapor pressure, but I think that they also have a higher viscosity, probably slightly worse diffusional characteristics. So other than that, it's I'm just thinking of temperature is going to make a difference. People check low temperatures for batteries often. If you're studying like dendrite formation, right? So low temperature inhibits diffusion. It's going to be worse at low temperature, and high temperature is going to go quicker. Is that in line with what you're thinking? I mean, those are just a decent list of stuff I can think of that would affect it.
Yes, I was thinking also regarding any solid the electrolyte interface.
Yeah,
Because that's why we try to avoid any if it has to do with the carbon base, you create SEI easier, right?
that's right.
Because
Yeah.
of degradation of the electrolyte.
So, yes.
So yeah, so do you recommend using like electrolytes that are based on non-carbon or based on carbon?
For the electrode, you mean?
Yeah, not for the electrolyte.
You mean based on carbonate?
Yeah.
I found carbonates to be very nice to work with. Ethylene carbonate, dimethyl carbonate, diethyl carbonate, methylene carbonate. I find them very nice to work with. They do help. So the SEI is a mixed bag, right? It's necessary, but it also is a degradation, so it can lead to problems sometimes if it collapses or stuff like that. You know, it's an odd balancing act that you have with a battery, especially on the anode, right? Because you often have to chuck some carbon in there to make conductivity improve. Carbon forms a very robust SEI. So the more carbon, generally speaking, especially if you have a pure graphite electrode as your anode, which most commercial batteries use, you have a pretty substantial SEI, which is in and of itself a decomposition of the electrolyte and prevents further decomposition of the electrolyte. And those decomposition products in a carbonate electrolyte, to your point, Carlos, is that it's a lot of, people have done characterizations of it and nobody is 100% sure exactly what it is, to be honest. It's a lot of stuff. It's like decomposition products, but carbonates are good, like decomposition fuel, if you will. They work pretty well for that. So I do have, whatever you'd say, positive sort of recommendation of using carbonate salts. And frankly, there's a lot to compare to in the literature. Like almost everybody, to my knowledge, uses carbonate salts with their lithium-ion batteries. So it's about as favorable a diffusional solvent as you can probably use, would be my guess, for lithium, at least for lithium-ion.
I see. Okay, I understand now. Thank you so much. I think that was my only concern for now.
Okay, well, we can sort of like let you. I mean, we can mute you or something, or you can hang around if you have another question later. You know, that's the benefit of joining us here, and you can talk to us. It's easier than typing through. So,
okay, thank you so much.
Yeah, thanks for joining us. We really appreciate it.
Yeah, thank you so much. Yeah.
Okay.
All right.
So
Good.
very cool. All right, let's so should we let's see, should we just we'll sort of keep Carlos out of the stream for now and kick him out on the yeah, so Carlos, you can type it. If we can't hear you, Carlos, if you have another question, just type into our little private chat here and say, hey, I have another question, and we'll sort of bring you back into the fold. But let's get to some of these other questions. I think there's been a few since the beginning here.
Let's see. The first one is from
There it is.
Doa. Please discuss the importance of nickel foam electrodes and
It's in gel.
gel or GEC.
Oh, maybe it is GEC.
I don't know, in electrochemical sensing, and also elaborate which working electrode is preferred when modifying material is metal oxide.
Metal oxides work well to cast onto glassy carbon. I did that when I was in graduate school.
The glassy carbon is the preferred working electrode material
I
when
mean,
you're working with a metal oxide.
carbon in general,
Yeah.
I would say, right? Because it depends on what your form factor is. So
Yeah.
if you're doing a rotating experiment, like you know, the sort of screening of your catalyst for ORR or whatever you're doing, may not be ORR, right? But electrocatalyst screening, you're usually using like a disc of something and casting it onto glassy carbon is always a good choice. Because glassy carbon just doesn't really do anything. It's really quite inert, and it's a poor electrocatalyst of a lot of common things like ORR or OER or AGR. It will do those things, but not very well, so that its impact on your measurement is negligible. And of course, you do a background on just the glassy carbon before you put your thing on it, right, or whatever.
Yeah.
So you'll have to also comment on
Yeah, I don't know what
anesthetic. What is it here? I'm not sure if I know what GEC and electrochemical sensing. I don't know what that is.
Yeah.
As far as the importance of nickel foam, I don't know if I can speak to that. I mean, foam electrodes, generally speaking, I can say offer a benefit compared to other, as a typical electrodes, if you will, like discs or flags or plates, right? Is in that they have a tremendously increased surface area. So if you're trying to get like product generation, right? You're doing some sort of electrolysis reduction to produce a product. Foam electrodes are really great for that because it's a huge amount of surface area, right? And so you can generate a lot of product that you might be sending off to a GC or an MS, what have you, something of that nature. It's a really great system for that. What it is not great for necessarily is that its diffusional properties, characteristics are very, who the heck knows, right? It's all over the place, right? It's very porous. It's not a, if you're trying to characterize something in a very well-known, if you will, manner, hydrodynamically, foam isn't going to work because it's like you might have only a rough idea of what its actual surface area is. Maybe you do BET analysis and you kind of get a decent amount of its specific surface area. But that's the downside in some sense. If you're trying to get like, I don't know, proof of concept, like does it catalyze a thing? You might just get like some, like your second part of your question, like some powder, deposit onto a glassy carbon disc or a carbon paper, some kind of carbon substrate will work pretty well for you. Carbon paper, carbon cloth. There's a few other probably
just large area electrodes and stuff.
Yeah, and then put your thing on it, and you have a film or whatever. You either spray it or you paint it or you drop cast it. There's a lot of different kinds of methods, but carbon's a good choice. For that. I don't know if you have anything to add. That's kind of
no. I mean, the other thing I would just say is nickel also has, I think it's in the same column as like platinum and palladium for like catalytic activity. So some people use nickel just for doing like bulk electrolysis type experiments, things like that. That's what I would say mostly a foam electrode would be good for. They can detect things, but as Neil was saying, analytical techniques, cyclic voltammetry, rotating disk, you're not going to get the best quality data basically from it. So, but you can electrolyze it, whatever you're doing to it. So I don't know if it's good for sensing because most sensors are usually relatively small area electrodes that have been well characterized, and then they're using it to detect small quantities, parts per million or parts per billion of some analyte or whatever the concentration they're looking for. So
I guess that's probably a good point because in the context of sensors, it's not as much what I mentioned about like generating a product and whatever. That's a like a synthesis.
It'd be a good synthesis
apparatus or something. But in the sensing application, maybe that's not as applicable, right? Because you don't need to generate a ton. You just need to see if anything's there at all.
Yeah.
Right.
Yeah.
So that makes more sense.
All right. Hopefully that was helpful. Moving on. I don't know if we take a look at all these things. Some of these, I'm just looking down at some of the questions just because there may be some overlap, but Raul is asking, can you explain cyclic voltammetry, principle and application? I think we can do that. We can easily spend a lot of time because cyclic voltammetry is a fairly, is this just the YouTube video? Yeah.
I just posted a link to this amazing YouTube video that my colleague here made that answers your question in about 11 minutes.
Yeah, and it has lots of animations and pictures and all kinds of stuff like that. So that will at least tell you a little bit about the principles of it. I would encourage you to watch that. Not to defer the question, but I can. One thing that we don't talk about in that video is at least the applications. Yeah. I think most people use cyclic voltammetry as like somewhat of a screening technique. It's like I have a molecule, some redox active molecule of interest, and then I sweep the potential to find the potential with which the redox potential of the species. And then it has some analytical you can quantitatively determine things like the diffusion coefficient, or you can use it as an analytical technique. And if you know the diffusion coefficient and the area of the electrode, you can say determine the concentration of a species in solution. So it's really a tool for analytical chemistry and looking at electrocatalysis, onset potentials. So it gives you thermodynamics and kinetics information about the molecule of interest that you're looking at. And if you have any specific questions, like after you watch that video, please let us know, because I think we'd be happy to discuss it in more depth.
Yeah. Unfortunately, this is one of those things. I think
It'll take a lot of time.
Yeah, honestly, I always feel bad sometimes evading the question, but it's like you literally spent a lot of effort to put together this really nice 13-minute concise video that explains exactly that question.
Yeah.
So we can either spend 13 minutes right now
Trying to do the
not
same thing.
covering it with the same level of precision,
Yeah.
or you can literally just watch that video. Yeah, but I think mainly the application of it is what you said. It's a screening thing, right?
Yeah.
You're looking to see where there's a Faraday thing happening.
Yeah.
Or if there isn't one. Because a peak in the cyclic voltammogram is like a semicircle in impedance. It means something's happening.
Yeah.
Right? Some Faraday thing is happening. And no peak means there isn't anything happening, and then you don't have any, it's just capacitance, whatever,
Yeah.
generally speaking. So
I would also say that I do want to get we can talk more about the principles of cyclic voltammetry after we get through some of the other questions.
yeah.
I think that would just be fair, because it can just take a long time going through
That's
some of it.
probably true.
Yeah. All right.
Next we've got here, Dua has another question. So I want to understand the concept behind increase in oxidation current with increasing scan rate and shift of peak potentials towards positive windows. So the first one is pretty easily explained by, I think, the Randall-Septic equation.
Correct. I don't know if it gives a conceptual understanding why the scan rate
Yeah,
increases.
I always find the explanation for this to be odd, because it's very mathematical. Let me share.
Yeah.
Window, draw a thing for you. Can you make sure I'm sharing or whatever?
Yeah. And then we'll go
Oh,
to
this.
yeah. And we'll minimize your question.
Yeah.
So that we can see this.
Inking. Okay.
Inking.
So the text box, that's it. So Randall's, so that's not Randall's
Yeah, I think so.
So basically the Randall-Septic equation, this is the way that a lot of people tend to answer this question. So I have it on another window because I don't know what's really perfectly.
Yeah, there's a lot of parts of it.
It's basically with respect to a peak current, but you can think about it in terms of regular current too. Because the equation you would do would via capacitance too is with the scan rate, but this is basically 0.44. It's like 446 something. Let's see what we got. We got NFAC. All right, so this is a fundamental electrochemistry equation, and then we have
Some diffusion coefficients.
we got NF NF T over RT. It's like 1/2. All right, so basically this is the Randall-Septic equation. So very simply, the answer to your question can be explained this way. This is scan rate, this is current. If scan rate goes up, current goes up. There you go, next question. So honestly, that's kind of one of the ways that this is answered. Basically, current and peak current essentially goes up with scan rate because just mathematically there's a direct relationship. There's another way that it's described as far as a peak current too, and I feel like I've never had a full grasp on this explanation like pedagogically. It's like it's about when the peak starts.
Oh, like the onset?
Yeah, the onset, it doesn't have time to relax, right? So the peak goes higher. I always have a hard time saying this the right way. But when you get a peak, right, when you're scanning and you get a peak, right, going this way,
Yep.
This right here is the Cottrell equation.
Uh-huh.
It's the Cottrell response. I'm sorry, that's wrong. That's the opposite. This is the Butler-Volmer. This is kinetics. This is the Cottrell.
Oh, okay.
Right,
Okay.
diffusion
That's
response.
that's a very interesting way of
Yeah.
looking at it. Yeah.
That's how
Yeah.
I do it in my R&D work, basically.
Yeah.
But this increase in the kinetic increase here, when you're scanning faster, that happens quicker, right? It's condensed. It's more condensed in time. So like this increase happens faster, and so diffusion is basically the kinetics is like Butler-Volmer equation is I is equal to, e to the thing minus e to the thing.
E to the thing.
Yeah,
Why is e to that? One
listen.
minus alpha the thing.
Yeah, but basically it's a function of over potential, right? Yeah. This is the Butler-Volmer. This is the most technical thing you've ever seen, I promise you. Okay, so this is Cottrell. The Cottrell equation is I as a function of time. I think the explanation usually goes something like this. It's because it's a function of time that I've heard this described like by professors or something, and it's like it made sense in the moment, and I feel like I could never get a grasp on the right way to like express this, but it's like the time because it's so fast. How does it work? It's like the relaxation of the it's like the kinetics has. I know I'm not doing this well, and I apologize.
No,
When you scan really slowly, it's like as you step up the potential, going really slowly, it's like at every potential, the Cottrell response is like it's like this, right? It's like settling down. So it's like if I were to step the potential here, my current response would be like, right, and then I step up the potential again. If I did a bunch of like potential step experiments, right, the current is decaying. It like decays down, right? So if I just go really, really fast, the current doesn't have a chance to decay down. So it like stays artificially high. It's something like that. It's like you're not giving the diffusional stuff enough time. So the fast scan rate just means there's less time. And so the current gets higher. Something like that.
Yeah.
And again, I'm sorry if that's not the best like wording of it, but that's in the ballpark of how I've heard it described by someone else, and I'm doing my best to kind of regurgitate that. And I think it's something like that. But that's roughly speaking, other than just a simple like look at the math, one goes up, the other goes up. So something along that line. It's like it's the faster the scan rate, the less time there is for relaxation of the current, and so it's just higher.
Actually, I think that's actually a really good explanation. Yeah, it's because there is a relaxation, sort of say, like in the Cottrell equation, the current decays with a t to the 1/2. Actually, one interesting thing that's in everything that Neil said with like the Randall-Sepsis equation is that the time has a t to the 1/2, and even with the scan rate, there's a scan rate to the 1/2 power.
Yeah.
Now, the other reason why the current increases is as the scan rate increases is also due to capacitive current. And the interesting thing about that is that there is a direct correlation. It's not a scan rate to the 1/2. It's directly proportional to the scan rate. So the current associated with double layer charging has a linear dependence on the scan rate. So your increased current with increased scan rate is both the Faradaic component from the Randall-Sepsis equation as well as the non-Faradaic component with the double layer charging.
Actually, that makes a lot of sense if you think about it in terms of, I'll do one more little math thing. I think this might make sense.
Yeah.
And if it doesn't, I'll just ramble for another couple of minutes and then we'll move on.
Yeah.
But the impedance of a capacitor, so you're talking about a capacitor, like you said.
Yeah.
Right, it's minus basically J over X. Right? Forget about the minus and the J. The point is it's an inverse relationship with frequency, right? So you can think of fast scan rate as like high frequency. As this goes up, this goes down, right? So so the first thing to say here is that as for this non-Faradaic charging process, as the scan rate goes up, my impedance of my double layer, let's just call this DL, right, goes down. Well, if you think about Ohm's law, V equals IR, or Z, right?
Or
So
Z, yeah.
these are basically the same thing, right? So as R goes down, I goes up. Right, for V is the same, basically. So maybe I should solve, right? I should solve this the other way. So I is equal to V over R, right? So, or Z, right? V over R or Z. So as the Z drops when you scan faster, it's the denominator, right? So the I goes up. So capacitively, thinking about it that way,
yeah.
The faster you move, basically, the lower the impedance or the resistance of that capacitor, your current the resulting current is higher.
Yeah.
So that's another
way to look.
somewhat unsatisfying if you just math. It's just math, right? But for what it's worth, that's also a decent answer.
Yeah.
Related to the unfair thing that you mentioned.
Yeah. I don't know that much about the last part of this question. Was shift the peak potential
yes,
towards
yes.
positive window.
Well, I mean, so if your peak is shifting as your scan rate increases, it indicates pseudo-reversibility
and
or slow kinetics.
it also represents some potential uncompensated solution resistance.
That too. Yeah, there's a number of things.
There's a number of things
Yeah.
that it could
So
be.
yeah, so it could be uncompensated solution resistance. If you're scanning faster and your peak is shifting, or the split shifts worse, or the peak shifts further apart, it could be uncompensated solution resistance. That's a good point.
Yeah.
It could be that it's not a very well reversible reaction, right? Pseudo reversibility or something of that nature, right? Or kinetically slow, which is somewhat of the same thing, I think. Right? If it's really kinetically fast, it's probably pretty reversible. Or sometimes you just have not reversible, processes or something like that.
Yeah. Yeah.
But that's usually the reasons why a peak is shifting with scan rate. In theory, if the Randall-Sepchik equation is being followed, perfect, like one electron, fast kinetics, all those sort of assumptions, then the peak of the peak with scan rate should increase but remain in the same potential. It should remain in the same potential but just increase with scan rate.
Yeah.
But it shouldn't shift forward. That's not dictated by the Randall-Sepchik. So that's some of the other things that we talked about.
Yeah. Doa has, I think, some more follow-up questions. Sometimes when we're repeating cyclic voltammetry experiments, there is a difference in current, even though the catalyst loading and scan rate is the same. Kind of explain what happens in electrochemical sensing. Well, getting the different current when you're cycling back and forth multiple times is somewhat normal. To a degree, I have observed a level of irreversibility where, whatever the process of the oxidation or the reduction, in this case, I think you're doing oxidation, it irreversibly sticks to the surface. And so you're not going to get the same current until, sometimes people have cycled multiple times and you eventually reach what I think called like a steady state where there's no change in like the anodic and the cathodic waves and everything is normal. So getting small differences in the current with each experiment, with each cycle, I think that's pretty normal.
That's really normal. Yeah, I mean, honestly, in addition to what you said, it could be any number of things. Like you could have particles delaminating from the surface too. You don't necessarily see them. Maybe they're small, so you might have actual physical particles leaving, and so your surface area you think it's the same, but it's actually changing ever so slightly because something is falling off.
Yeah.
It happens. Something sticks to the surface, or an oxidation state, or something of that nature happens on the surface of your catalyst with subsequent scans, and eventually it settles into some state, but maybe in the first few you have some change of like a surface state, or you get some hydroxide that forms at the surface that sort of messes with it. It has slightly different conductivity than the original catalyst material. Like there's a lot of possibilities here, right?
Yeah.
But even when you think what you have is identical, it really isn't. There's just no way. You're polarizing and changing and doing electrochemistry on it, and as a catalyst, in theory, it shouldn't really be changing, but it does to some extent.
Yeah, and your system started in air. Like you prepared your catalyst in air. There's all kinds of stuff in air that gets on your electrode, and once it's in solution, it's it's different. Those
Yeah.
things may be coming off. That will also be in your cyclic voltammetry data. So there's a lot of things, but yeah, having slightly, we also need to know exactly how different is the current, you know?
Yeah, if
That's
you're
another
seeing it
question.
just sort of change a little bit subsequent scans, like that's like Alex said, that's perfectly normal.
Yeah.
You know, and often one of the kinds of characteristic tests that people do, or even as like you call it like electrochemical cleaning as a whatever means of
Prepping the
Yeah,
solution,
yeah,
or
or-
prepping the electrode.
exactly. You literally do that. You scan 100 times back and forth until it repeats on itself. So you know you have like a set surface, like it's a right, it's a reproducible surface, something of that nature before you, I don't know, inject your reagent that you're trying to sense or oxidize or reduce, whatever you do.
Yeah, the catalysis thing.
Exactly.
Hopefully that was helpful. All right, next question is from Ranjiv. In what range should the goodness of fit values be for an ideal EIS circuit fitting? Now, I feel like this is going to be one of Neil. This is just like trigger chi-squared values for Neil. It's just like
I'm going to handle this with happiness and grace. Thank you very much. Yes, I do get this question a good amount. I try to answer it. Hopefully, if you've joined us, you know that I do my best to not shirk away from questions, should we say. You know, if you ask me a question, I'm going to try to give you a definitive answer, and I'm going to try to be numerical and give you answers if I can. So I do my best to not hand wave questions and not answer them. That being said, stop asking this question. No. So to be honest, first of all, it depends on the software you're using, right? So I have knowledge of my company's, software and goodness of fit. I think like Gamry, for example, I think their software uses that terminology, maybe biologic. I can't remember. Right? Every company has a different terminology for what they use for this phenomenon, which is when you're doing a circuit fit in EIS, how good is it? Right?
Yeah.
Ultimately, you're trying to answer that question. They are all calculated ever so slightly differently, but with respect to a circuit fit, you can visualize it like I've got my experimental data. This is my experimental data. This is my fit.
It's actually a very good fit in the sense of like describing
It's a little bit
experimental.
different enough.
Yeah, it's just a little bit different than
Listen, much like Anakin Skywalker, my drawing skills have doubled since we last met. Remember that line?
Yeah, I do.
That was episode 2 or 3.
That was.
like-
I'm not a big Star Wars fan, but that was
I'm not a Star
episode.
Wars fan either, and part of it is because the dialogue is so stupid. I can't even deal. It's like
It was
someone
episode 3, Anakin versus Count Dooku.
Oh, so there it is.
Second time, and
like who thought that was a good dialogue? Not like he can't look at him and say like I'm stronger than when you last fought me or something like a normal person would say. Like my powers have doubled. Oh, doubled, you say?
yeah, double.
Well, I mean, if you only went up by 1.6, I could take 2x.
Two.
It's over. That's why you won. 2x. Double.
Remember, they're from like another galaxy, from a much longer time ago.
That's
so
how they
spoke
talk on
differently.
Tatooine or wherever he's from. The ice planet.
They were outside of Coruscant, I think.
I'm not actually a big Star Wars fan.
I'm an okay. I wouldn't call myself like a hardcore Star Wars fan, but I do like me a little. The new one's not so much, but the
I watched
original.
The Mandalorian, and the first couple seasons were pretty good. This last season was awful.
Oh really?
Yeah, I liked it for a while, and it kind of fell off a little for me. But
Comment if you guys are Star Wars
I'm a
fans,
Star Wars fan or
and
Mandalorian.
whether or not you find how EIS and electrochemistry play in your Star Wars experience.
Yes. Do you take into account the force when you're wondering if your experiment is working or not? That's critical.
Yeah.
So
I
okay,
find your lack of chi-squared.
I find your lack of
Disturbing.
circuit fitting disturbing. So, so
All
the
right.
chi-squared, or
Goodness.
goodness gracious me, goodness of fit. These are all, as far as I'm aware, similar phenomena.
Mhm.
You have experiment minus fit, so it's usually something like it's a sum of the experimental points minus the fit points squared. That's where the square comes from. Divided by like either the number of points or maybe it's divided by the experimental, so it's like normalized. There's some normalization, but this is the point: is that there are some different ways you can do it. To be honest, so the way Pine does it is different from the way Biologic might do it, which is different from the way Gamry might do it. So it's like if you're doing a circuit fit with Gamry and you get 0.1, and you do it, and then you load the data into Pine software and you get 0.01. As much as I would love to say this is the case, this does not mean that like Pine software did a better job than Gamry software. That's not what it means. They're calculated differently. So the first answer that I give you for this is that you, generally speaking, when you're trying to figure out what a value is, it's hard to do that in a vacuum. Meaning it's hard to answer that question by saying like 1 or lower. It doesn't really exactly work that way. It's not easy to. Now, when it comes to Pine software, I can tell you, generally speaking, I like to say about 0.1 or lower, but there's variation on that as well. But as a some, I don't know, frame of reference, something like 0.1 or lower with my company software, that's all I can really speak to, right? If it's much higher than that, it probably means you have some outlying points or some sort of poor fit going on. Okay. The most appropriate thing to do, though, however, is compare similar data sets. So what I mean by that is like you have one data set with the same amount of data points, and you're comparing 2 different fits. Like, okay, I have this fit. Well, I'm going to fit a Randall's element and a Warburg. Okay, whatever, and that gives me something. But well, maybe that's not what I want. Maybe I should do 2 Randall's elements, and then I'm going to fit that. Then compare those 2 goodness of fits or chi-squares between the 2 different circuit models on the same set of experimental data. That's a true comparison, right? Then you're getting, well, one of them is lower. And so that would at least more definitively indicate which circuit fit is more appropriate for doing a better job. That's probably a better way to apply this kind of thing. And again, it depends on the software, but like you might do that, but both of them have a chi-squared of like 80 billion. Well, they're both probably garbage. So there's some subjectivity. There's always some subjectivity to this because exactly what the value should be, it's not always clear.
Yeah.
So I hope that addresses the question to the best of my ability. I didn't get that triggered.
That's good. Yeah, you did good.
See, I can do it.
You done good.
Nobody asked me about looping capital.
Looping capital. All of our electrochemical trigger points. Okay. Discuss about LSV and how LSV is helpful for PEC reaction. What is PEC reaction? And this question is from Tamil. So
Photoelectrochemical cell?
Photoelectrochemical reaction?
Is that like which one? I mean, a specific one or just in general? Is that what I assume you mean photo?
So Tamil, if you want to, if you're listening, if you want to clarify a little bit about that, if you want to clarify a little bit about which LSV refers to linear sweep voltammetry, or we know about that, but PEC sometimes can mean different things. I actually, if you are asking for a photoelectrochemical reaction, LSV is usually it just helps you generate an IV curve, which is typically used when you're doing a photoelectrochemical reaction and you want to see oh, what's the current as a function of voltage. You would just sweep the potential. Oh, just hit some other.
Yeah, it's another.
Sorry, person.
I think this mic is on too.
Oh, it is on. Oh, I guess
this is our third chair.
Yeah.
Yeah.
If you want to join us in person,
someone come join us in our. That's like next level. Thanks. Joining us on Restream and then joining us in person.
But most people just do linear sweep voltammetry, very low scan rate in a photoelectrochemical reaction.
Yeah.
But most people are actually just holding the potential at some point and then turning the light on and off in photoelectrochemical reactions and then seeing if they get a current response. Does the current increase when the light is on and off? So that's mostly what people are doing. So yeah, LSV is really only helpful for getting the IV curves that people publish with a photoelectrochemical cell. So that hopefully, Tamal, that's helpful, but also ask for more clarification if you need it and tell us a little bit more about.
I want to add one thing to that as well.
Yes. Oh, it is a photoelectrochemical reaction. Okay.
Let me find it here. Keep talking.
Oh yeah, yeah. So
I have a sample sort of
oh, from the solar
power
cell.
curve, solar cell something. I'll just illustrate one quick one. I gotta track it down.
Yeah, that's fine. We can. I'm gonna take a look at least at another question from. So let's see. Which is the more efficient way of loading catalysts on nickel foam? Is drop cast method or hydrothermal method, where you put nickel foam in precursor solution? So I would say it's either going to be, in my opinion, a hydrothermal or a precursor solution. You want to, nickel foam is big, it's big surface area, maybe even solution. You need, for all of the foam to be, to load the catalyst onto the nickel, it needs time for every bit of the catalyst to get on the nickel. And I think it would also give you a somewhat reproducible technique for loading onto the nickel foam. So drop casting onto a nickel foam is kind of iffy. I think it lends itself to uneven loading.
That would be a mess. It'd be tricky.
But like putting it into a solution and letting it sit for a known period of time, looking at the weight difference before and after, drying it, I think that's a much more consistent way of loading a catalyst onto your nickel foam. I don't know that many methods for it, but I would say you want uniform loading and methods that involve the entire electrode getting submerged in the catalyst or the pre-treatment, the precursor solution is the way to go. Did you?
Yeah, I'm gonna pull this up. So just to
we're gonna go back to this.
Tamal's question about LSV for photoelectrochemistry. I'll just show you quickly here. I have a solar cell, so it's like a photoelectrochemical thing. So this is an example of exactly that. So this is an LSV. It's sort of backwards from what you'd expect to see. Down here is the current and up here is the potential. When you do the test, you actually get it the other way, right? So this is like a cyclic voltammogram. This is an LSV. So I started at open circuit, which was like 1 volt, 1.5 volts. And this is just like a commercial solar cell. And I drop the voltage down and I start getting currents out of it, right? You get, in this case, I got 6 milliamps. Okay. Of power, right? My solar cell was helping run some device. Okay, so you flip the axes, and then one of the things that you do, for example, one of the applications, let's just say, of an LSV, why you do it, is to get a power curve. So what I would do is I would take the XY product. Just have it. Okay, so this is another thing that people do with fuel cells and photoelectrochemical cells is from the LSV, if you think about the units here, right? Potential and current. Well, this is E times I is P is power. Right? So when you multiply volts and amps, you get watts or milliwatts, whatever. So a power curve is another application of a fuel cell or a solar cell, because sometimes with a fuel cell, you're trying to figure out, well, how much current can I get out of it when I drop the open circuit voltage and put a load on it. And the other is, well, what's the maximum power? Because I'm trying to move a car or a bicycle or a moped, whatever. Like a device usually requires a lot of power, right? That's the key to make an engine run or something like that. So you're trying to find that potential, and it's not like always intuitively the lowest potential, right? You start getting more current out, but you run into diffusional effects and stuff like this. So it's not intuitive necessarily that the maximum power is at the highest current, lowest potential. So a power curve is the multiplication of the axes on your LSV for a photoelectrochemical cell, and you get a peak, right? So this would be like, oh, my maximum power is whatever, 8 milliwatts for this terrible photocell. So that's the answer for you.
Very good. Very good. All right. Moving on. Doa has a lot of questions, and we're getting to them. What is the difference between diffusion control process and adsorption control process?
One is controlled by diffusion, and the other is controlled by absorption.
Exactly. That's the main difference between those two processes.
I'll be here all day.
I mean, actually, in a way, it's kind of true. So I think it's best to understand this. It's almost better to just kind of define the terms and then think about what they mean. So diffusion is the random motion of molecules. It's a representation of how quickly does a molecule move through solution or through media or through whatever it's through, it's moving through. Adsorption is when a molecule adsorbs onto a surface. And so one of them, adsorption, is in most cases, it's a self-limiting reaction. And it's limited just like once it absorbs, it's on the surface, it's done. But, and that is gonna be the limit to whatever the process is. So sometimes if you're looking at surface chemistry, like I'm going to adsorb a monolayer of molecules electrochemically, your process is limited by the adsorption of the molecule. So no matter how long or how fast, no matter what scan rate you use or step potential, your current response will be limited by the adsorption on the surface. So you could increase it by, say, it may be increasing the concentration will increase the rate of adsorption, or changing the area of your electrode will also change the adsorption. And diffusion controlled it's a form of mass transport. So actually, they're kind of two different things in a way. But diffusion is a mass transport, it's a mode of mass transport. So when it's diffusion controlled, it means the only flux of molecules towards the surface or towards anything is through diffusion, through this random motion, which means that your limit in terms of the current or getting molecules from point A to point B is just going to be based on how they naturally move from point A to point B. It's not based on migration. It's not based on convection. So migration, the movement of molecules based on an external electromagnetic field, and you're not moving them through things like stirring, physically moving the molecules. So hopefully that gives you a little bit of explanation about a diffusion versus an adsorption controlled process. Right, so let me know if you have any further questions or further elaboration on that kind of question. But it's like, yeah, diffusion's diffusion controlled and adsorption's adsorption controlled.
Yeah, next we have Utsuho does science. It's good to know.
That's good to know.
Yeah. So this question is, I would like some pointers where I can find information of electrolytic creation of different iron oxides versus reaction conditions, making a crude ECM machine. Electrochemical machining. Electrochemical,
Maybe.
something like that. It would be very helpful. The second part of this, I think, says,
Yeah.
I've observed that a lot of variables affect what oxide I will get, but I have no idea which variables are most important. Potential, current density, electrolyte. So probably potential, but the other ones matter. So
Yeah.
So I can't speak. I don't think either of us know much about electrochemical machining specifically, or frankly, I don't know like
Corrosion, oxidation, like
well,
different iron oxides. Right?
yeah. I mean, so first of all, which variables are the most important? So you listed potential, current density, electrolyte composition, and pH. So 3 of those 4 are really important. The other one is not. The other one is more of a, I shouldn't say that. The other one is a byproduct of the other. So
yeah.
So current density, it depends. If you're running your experiment with a controlled current, then you do need to care about current density. Otherwise, the current density is just what you're measuring. So most
Yeah.
likely you're choosing a potential that is going to drive which reactions occur. Current density is what you're observing. So I wouldn't consider current density to be of the most importance. It will matter because you could, for example, calculate how thick of a film you made if you know the stoichiometry of what you've done. You know that, iron plus 2 plus 1 electron goes to iron plus 1, or iron oxide. You could you could use Faraday's law of electrolysis to determine the mass of iron whatever that you made based on the current produced. But as far as which oxide is being made, that's mainly based on potential and pH. And electrolyte composition and pH go hand in hand, right? Because if you have a strongly acidic, solution. As far as pH and electrolyte composition, electrochemical reactions shift by a rate of about minus 60 millivolts per pH unit. So what that means is if you're at neutral pH 7, right, and you bring it to pH 1, right? So you go down 6 pH units, right?
Mm-hmm.
You're going to be about 360, 350. It's technically 59, but whatever.
Yeah.
You're going to be about 300 plus millivolts difference. Now, the direction matters. So as your pH goes down, the potential goes up. So if you're looking at a standard table of potentials, it's usually at pH 7. I think it's sort of implied. Some of them are at like 1 molar sulfuric acid. You just got to check what you're seeing, right?
Sometimes you have to look at like a Porbet diagram.
Yeah,
Porbet diagrams actually contain all of this information.
Yeah, that's a good one.
So-
P-O-U-R-B-A-I-X.
Yeah.
Porbet. It's named after a French scientist.
And that will tell you
That gives
under
you
what potential and what pH.
Potential and pH, what species will exist. So I look up an iron Porbet diagram. Is the first is a good suggestion.
Yeah.
But another thing is, right, as we talked about, what are the applications of CV earlier, right? So it's like screening. So you might do some sacrificial tests, let's just say, where you like do a CV over a really wide potential range, and you get like, here's a peak here, and here's a peak here, here's a peak here. And that's like iron oxide 1, and then iron oxidation 2, and iron oxidation 2. Okay?
Yeah.
So it's like, to pick which one you're making, potential matters and pH matters. So the pH, like if you have peak, 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 and you bring the pH down, all those peaks are going to shift up. Vice versa. If you bring the pH up, all those peaks will shift negatively. Okay?
Yeah.
So that's how pH affects where the things happen. And then it's the potential you pick is where it really matters. So if you are above the oxidation potential of one process, but below the next one, only the first one will happen. But if you are above the oxidation potential of both of those, they will both happen. And maybe the second, right? So like, the standard potential of some process is a point at which potentials negative of it will drive the reduction, and potentials positive of it will drive the oxidation.
Yeah.
Right. And so you're talking about oxidation. So you're trying to create, presumably, based on your question, some kind of iron oxide. Right? So you're trying to create one specific iron oxide. So then what you're looking at doing is picking a potential, a critically, carefully chosen potential that is above the potential of whichever one you're trying to make, with a high enough so that you're driving the reaction successfully. The higher the potential compared to its standard potential, the greater the driving force for that reaction. But still lower than, or like if you're looking at the CV, before the peak of the next one, for example. And this is where it gets tricky, because what if the peaks are really close together? It's hard to pick a middle potential. That's a Porbet diagram.
Yeah, I'm just putting up a Porbet diagram of the of that, so you can see this will help you kind of look at and understand. Because the other thing that Neil's mentioning that's helpful for this is, I think the slope of some of these lines are going to tell you like, oh, this process, like pH is more important or potential is more important, because as the slope kind of changes, it's like, oh, I only have to move this by 1 pH unit, and bam, I've already moved from the iron 2+ to the iron, to this kind of iron hydrate, iron oxide hydrate formation. But I have to move the potential a lot, to get that same thing. So yeah, looking at this Porbet diagram will help you understand at what pH and at what potential. And this is just E naught, so I don't know what.
Yeah, well, sometimes what this does is it helps you answer the question like, well, if I want to go from iron, 2+ to iron 3+, there's no like looking at this diagram, there's no physical way to do that by changing the pH. It's a horizontal line.
Yeah, that's right.
You can only do that by increasing the potential.
Yeah.
However, if you want to go from iron 2+ to Fe2O3, I'm just looking at the diagram.
Yeah.
You can increase the potential at pH 6, or you can just increase the pH. You might like those at the same potential. So like these are just options for you for like experiment manipulation or creation. Create a solution at 1 potential and 1 pH, and you'll have. And looking at the Porbet diagram, you'll have whatever, right? So you can manipulate both of those to get what you need.
Yeah. All right. Well, hopefully that's helpful.
Yeah.
And stop sharing that. Okay.
Chris has a question here. Let's see.
Yeah.
So just how much overpotential in the plasma system, is required to maintain a lightsaber at a usable length and strength? Yeah, this is a really good question.
This is a very good question. I want to say it's definitely in the hundreds, maybe thousands of volts.
It's at least 1,000 volts. It might be 1,500 volts.
1,500.
The last time I ran my lightsaber, I think I used 1,500 volts, and it sliced through the roast chicken that I made for dinner. It was perfect.
Yeah.
But
you also have to check whichever Kydarian crystal you have.
That's
will
true.
Also change the work function
right.
required to.
And if your crystal is deactivated slightly, you're going to have to use a higher voltage to compensate.
Correct.
That's right.
Yeah. Enable IR compensation.
That's true.
And if you have the guards on both sides, that's gonna shift your potential.
This is inside the movie industry, but actually, when Anakin says my powers have doubled, what he meant is he just doubled the voltage.
Yeah, he doubled the voltage.
He doubled the voltage of his. He wasn't any better at actually fighting. He just doubled the voltage of his lightsaber, and then he cut off the guy's head.
Incredible! It was.
Yeah, he turned the knob up to 11.
Like that scene. Actually, when you think about it, it's like, wow, he had like double lightsabers across the guy's head, like decapitated. This is a PG. What's that? PG-13.
PG-13. I mean, they didn't show any blood or anything, but yeah, he just like, and then the Emperor goes, "Do it," and he's like, "Oh, okay." That's great. Okay, so thank you for these great questions. Very important.
We got
Wakar says, why couldn't I get good marks in electrochemistry ever? Because it's hard.
It's hard and it's unfair.
Yes, it's not fair.
It's like, actually, I'm pretty sure if someone gave me like a problem set to work out in electrochemistry, I'd fail at. Like I wouldn't do that.
It's like if I had to take like a PChem or organic chemistry or some of these classes again and do all the like
problems.
Like open up Barton Faulkner and open up a chapter and like try to do the problems. It's like, oh,
I don't want to do that.
I don't want to maybe later.
Maybe later.
I wish you tremendous luck in your academic endeavors, but I have great sympathy for you. Electrochemistry is hard. It's hard in practice, let alone in these theoretical problems. It's all tricky, man.
Yeah, it is.
You have our sympathies.
Yeah, we're sorry.
Yes. All right, Dua has another question here.
Yes.
There are different formulas to calculate LOD. What's LOD?
I don't know what LOD is.
Look it up all. LOD and sensitivity. So many acronyms. And sensitivity of working electrode. Minor differences in formulas. How to be sure which one is the right one? Sensitivity of working electrode.
Limit of detection.
I see.
Okay.
I don't know.
I don't know about calculations for the limit of detection, but like the ability to detect something electrochemically is based on a couple things. One is going to be your potentiostat and your electrode range settings. Yeah. Right? You are the electrode range, basically like how a potentiostat measures current, is based on passing a small voltage through a resistor that is known, and we use Ohm's law to figure out what's the corresponding current. And depending on what that resistor is and how much, how much actual current is there, is going to determine how much you can detect. But then the sensitivity, like, does an electron transfer actually go through? So sometimes the limit of detection for certain electrodes, like, for example, there are these mercury amalgam electrodes that can detect lead very easily because the lead actually embeds itself into the mercury. And when you do an anodic stripping experiment, you're actually able to detect a ton of lead, like even small amounts of lead, because they embed themselves into the electrode, actually allows you to detect like parts per billion of lead, which is really small. So the electrode range and then the sensitivity of your electrode for that specific analyte is going to determine kind of your limit of detection. I think general equations for the limit of detection that's used around all analytical chemistry will be useful in figuring out your LOD for electrochemistry and your electrochemical sensor. And then, yeah, just kind of like, if you're able to detect something with your working electrode, try to go to smaller and smaller and smaller concentrations. And then similarly, you will also need to protect your system with maybe things like Faraday cages, because you can start getting noise from like electronic sources that will interfere with your detection limit. And certain electrochemical techniques are also really good at getting rid of some of the noise. So slower scan rates to remove background current, or sometimes even fast scan rates so that you detect something, can be a way to determine, to actually detect something, the lower limit of detection. So those are like parameters that you have to play with to see how low you can detect something on your working electrode.
Yeah. You're asking about equations. So I just found like 3S over M. Like, I don't really know exactly. I've worked with sensors because this is related to, I think, Jula has a question a little later. How do we compare, for example, sensitivity of values of electrodes? So like 180 microamps per micromolar per centimeter squared and 0.70 blah 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 amps. So this is apparently, and this is not something I'm very familiar with, so apologies here.
Yeah.
But it's like, or absorbance. Is it absorbance units or microamps? Again, I think you mean absorbance units. Something like that. But it's basically, or maybe it is amps, I guess. But it's like the amount of amps per concentration per surface area. So it's like, I mean, how do you compare? Well, one of those numbers is bigger than the other. I guess it's better. I mean, if you're looking at a lot of different equations with a lot of, which one is right. Especially if, so what I would say is this, like, there's different types of equations in electrochemistry or in almost anything, really, especially in the engineering world. Like, there's the Butler-Volmer equation. That's like fundamental and true for the kinetics, right? The control equation describes diffusion. The Reynolds-Septic equation, heat current versus scan rate versus diffusion, blah blah blah. Mm-hmm. These are like true where there's assumptions baked in, but they're not empirical, they're theoretical, right? And they're based on first principles in thermodynamics and kinetics and that kind of thing, right? And then there's stuff like engineering equations, right?
Oh yeah.
Like the Eisenberg equation for like rotation rate of cylinders and the Reynolds number, and like there's engineering tools. So what I would say in general, without more specific knowledge of limits of detection equations and like what these numbers, like which one of these numbers is right or wrong or which equation to be using, without knowing specifics, you just have to differentiate between whether this is a fundamental first principles equation or it's an engineering equation, because engineering is made up. Okay, and I mean that First of all, because it's funny, because
Yeah.
it's literally just like, hey, if we just raise this thing to the power of 0.27, it works. Cool.
Yeah.
What does it mean? Who cares? It works.
Yeah.
So the first thing is that, wow, that's funny. It's actually important to be cognizant of that. These are most engineering expressions, if this is what these are, is made up. So there isn't really an answer necessarily to which one's right or wrong, because a lot of times they're right for specific situations. So even, for example, like the Reynolds number, right? As one example that I can think of, like Reynolds number describes fluid flow. And, you know, for example, like flow through a pipe, if the Reynolds number is less than 2300, it is laminar flow. If it's between 2300 and 4000, it is a transitional period. If it's over 4000, it is turbulent flow. Okay, we can conceptualize the difference between laminar flow, very smooth, nice flow through a pipe, and turbulent flow where it's going crazy, right? And if you're doing calculations on fluid dynamics, you cannot use the same empirical engineering made-up equation for laminar compared to turbulent. You have to use a different one. There's a different exponent. There's a different whole silly little thing, right?
Yeah.
So for you with limits of detection or whatever, the first thing is just to make sure if it's a fundamental first principles or it's an empirical kind of thing. And then second is to try and make sure that your experimental conditions, whatever they are, match the empirical assumptions of the equation that you're using. And then honestly, it's just picking the one that most appropriately fits to what you're doing. You know, if there's some limit of detection equation that, you know, assumes some turbulent flow pattern and you're not rotating or moving your electrode at all, well, that probably doesn't apply to you, even if you think it gives you a good, you know, result or something. So maybe there's one that has a, you know, an expression that takes into account something that is related to your experimental system, and it's more appropriate. So try to do those kinds of matching, you know, phenomena. I guess I don't know how much better to put it, but that's the best I can give there without, honestly, unfortunately, knowing specifics about these things. And I see Chris gave a little bit of advice, which thankfully Chris is our surrogate electrochemistry professor here.
Yeah.
So start with calculated value at 1 micromolar and 1 square centimeter for each. Compare your sensitivity to noise floor. So yeah, so Chris obviously knows more about this than we do. So please consult with him.
Yeah.
Next question. Okay, so yeah. So thank you, Chris, for the input here.
Yeah, and also I'd like to say, Kanav stopped by the stream. Thank you, Kanav. I think we've been in some level of email contact. I'm glad you were able to kind of figure out some of the problems that you were running into, which is tough. I remember looking at he was getting all these different CVs, different shapes after like 50, 20, 30 cycles. And it's like, oh, there's some weird instability issues. Systems. I'm glad that you've sorted out some of those problems. Let's see. It looks like we have a question from Mari. My current project is about electrochemical detection of pesticides by using functionalized GQD. Oh, gold something.
Quartz.
It actually doesn't have a question, so I didn't. It's like.
I hope your project is going well.
Thank you for telling us that.
GQD, I don't know.
GQD.
QCM.
QCM.
Q is quartz. Gold, quartz. Diamond. I don't know. I don't know what GQD is.
I'm trying to see if I'm just making sure that we didn't miss any questions. Yeah. If we missed your question, just like type it. You know, we're gonna look. I have to look up through the chat, but if you type a new question, it'll be at the bottom of the chat, and then we can address some of these.
Yeah, and Mari, if you have a question related to your project there, please feel free to type it in. It looked like you left an ellipsis right there, so maybe you have a question forthcoming. So we'll watch for that. Watch for that if you have a follow-up. Looks like Kanav actually does have a question here. So they have one question: running CV with graphite electrodes, and sometimes despite the surface of the electrode being clean, I get weird noise. Not just in the sense of jagged lines, but the whole shape.
Okay, so
that sounds like a connection problem. I mean, again, it's hard to know without seeing the data, but
Yeah.
what do you mean? Like how jagged and how bad? Like if it's like all over the place, like a Jackson Pollock painting, it's kind of crazy. You know, you probably have some connection pattern or something else. But
Yeah, and I understand getting noise in like a spot. It's like, I get noise and then it looks normal. But if like the whole thing is there, if there's noise throughout the entire thing, there may be some electronic noise. Like I don't know if you're getting like a little bit of noise on top of the entire voltammogram. That may mean there's some instrument or electronic noise, and you just have to like filter it out. That's also a
so
possibility.
like there's different kinds of noise, like Alex is saying. So if you have like if your CV is going and it should look, well, I guess it's graphite, so maybe there shouldn't be any peaks, but just whatever, bear with me.
Yeah.
So okay, there's your good CV. That's happy. But maybe it's some kind of oscillating
Yeah.
fuzziness or whatever. So that's periodic noise. That could be 60 hertz noise or 50 hertz noise, depending what country you're in.
Yeah.
Okay. So that's usually a result of the power supply, like for the country, so to speak, the United States and China and a few other, I think China actually, or Taiwan. I always sort of mix up which ones are at 60 hertz. Most of Europe is 50 hertz. So one thing you can do is you can literally do fast Fourier transform on the current versus time. Like if this is current versus potential. So if you extract the current time curve and you find the characteristic frequency here, if this is like 60 or 50 hertz, that means if that's what the noise is or something, that's usually an indication that there's interference. So your cell cables might be picking that up.
Yeah.
Or in the alligator clips where it's not shielded, you can filter that out either with your potentiostat or after the fact you can apply a smoothing transform, clean it up, things like that. If what you're talking about is you have like this is like a dragon. Wait, it's
Tractor. Yeah. Sorry.
So you're welcome, everybody.
Yeah.
So, okay, so if it's really crazy like that, that's probably a connection problem. Like that, there's something is not connected properly. You need to check your reference, make sure everything's wedded, make sure there's no blockages. You know, graphite can be kind of hydrophobic in general, although it's obviously an electrode that works pretty well. But just make sure it's wedded properly, make sure it's in solution, make sure there's no, I don't know, something not touching, or make sure your cell cables are connected. A little, silly things like that.
Yeah.
Otherwise, I don't know what other there's ways noise can manifest, but
So Kanav is mentioning that the electrodes are preconditioned in distilled water, but they're also in 5 molar nitric acid, which is pretty strong stuff. If you're actually sweeping around an oxidizing potential, there's a chance that you're generating perhaps even micro bubbles that are popping. And so you can have this noise that's always around. And it's not like you see lots and lots of bubbles just kind of forming everywhere. They like form and then pop instantly, but they're tiny. They're really, really tiny. So you get these micro bubbles that can pop up if you're at these potentials where there's a reaction occurring. And 5 molar nitric acid is pretty strong. So that might be a thing that's happening.
Some electrodes are preconditioned with distilled water wash, others clean with 5 molar nitric. Yeah.
And they're big. They're large surface areas too. So you may even have stuff happening in the pores and the cavities. I'd be curious to know what happens if you have a glassy carbon electrode, just pure glassy carbon, well polished, clean surface. If you get that same kind of response.
I don't really know what that strong an acid treatment is doing. Maybe it's functionalizing the surface in some strange and unwanted way. Must be that. That kind of a strong acid treatment might be conditioning the surface in a way that is unexpected. Especially 5 molar nitric, that's quite aggressive. So the only way to really elucidate something like that would be to do like surface characterizations, before and after treatment and acid, something like that, right? Like not electrochemical, I mean like physical, like you do XPS or something on and see what the surface looks like, which is a bit tedious, but
Yeah.
you know, like before you do your electrochemistry on it, you can check if like, oh, did I change something really pretty dramatically, or you know, and then does that explain it, right? Because yeah, you said like you receive the electrodes, you kind of get everything. If you have the ability to get clean voltammograms with some electrodes in the setup, and then these ones, and the only difference is that you've done this sort of rinse or whatever, and they're behaving weirdly. I mean, all variables roughly the same. It does suggest that this treatment process is causing something that's, you know, getting in the way or something. Ultrasonic cleaner to make sure the bubbles don't stick. Yeah, that doesn't always mean they're not there though.
Yeah.
So,
Yeah.
For sure, that's a good idea, but that doesn't necessarily guarantee it, right?
Also, if you want to, like, Kanad, you have my email, so you can email me a sample of the data, and I can take a look at it. We can talk about it
In
next
fact,
week.
sometimes
or something like that.
ultrasonication can generate bubbles.
That's also
It's
true.
not ideal, but it can. Like you're providing energy into the small pockets could actually
Generate bubbles.
vaporize and maybe create bubbles when you're sticking.
Yeah,
Yeah,
that's also true.
so it's a bit unfortunate. Hopefully it isn't happening, but it could.
Okay. All right.
Yeah.
Very good.
Let's get to this one pre-prepared question
Yeah.
from Tarek that I can answer here. So this was a question about what's the right approach to connect and disconnect working reference and counter electrode in 3-electrode system. So my advice is always to make sure the counter electrode is the one that's connected the least amount of time. That's my general advice. So I don't think it matters too much whether you connect reference or working first. But what you don't want to end up with at all, if possible, is a situation where you have working and counter electrode connected to your potentiostat, but reference not.
Yeah.
That's where something dangerous can happen. Now, most commercial potentiostats, for example, like you walk into the lab, you prepare your thing, you get your setup, right? You turn your potentiostat on, you fire up the software, you do all this stuff, right? That turning on of the potentiostat, most companies, potentiostats are constructed and programmed in such a way that when you turn them on from nothing, they're idle.
Yeah.
But they're not doing anything.
And the cell is disconnected.
Right. Yeah. Yeah. Exactly. So it's like the potentiostat is on, but it's not doing anything. It's not applying anything. It's disconnected. It's actually like internally, physically, just like the potentiostat will actually have like a resistor disconnected or a switch or something so that it can't apply or do anything. So, you know, start experiment and tell it to do something. That being said, not all potentiostats operate that way. So, you know, you might have a situation where your lab mate did some tests yesterday and shut everything down and didn't realize that, you know, they didn't turn the cell off at the end of their day. You turn on the potentiostat and it's still applying 0.6 volts.
Yeah.
Something. You start connecting it to your stuff. You don't connect the reference electrode because whatever you have reference and counter, or working and counter connected. And it's like, hey, well, I'm applying 0.6. That's what I'm supposed to do, but I can't measure the reference. It's not plugged in, so I'm just going to go to the rails. And you just destroy your electrode immediately.
Yeah.
Now, that's a bit dramatic. It doesn't happen that often, but it can, and it has. So even in the case where you had a potentiostat that like was in a bad state or you didn't know it was on or something like that, if you connect working and reference first and you leave the counter electrode just hanging, not connected to your cell, the counter electrode will read. Nothing's still going to happen, even if the potentiostat is trying to apply, because it's not. There's no circuit. You're not connected. So the last thing you do when you set your system up is you connect the counter electrode. Now it's ready to go, and the reference is there. It's ready. It's connected. And then when you're done, you're putting it away. Disconnect the counter immediately, because then you open the circuit. It's the safest thing to do, right? You run the least amount of risk of like doing some crazy thing to your experiment, to your electrodes, zapping it or whatever. Now, this is an issue for a lot of time because most potentiostats are idle when they turn on. You run an experiment, and when the experiment's done, it just reverts back to its open idle state.
Yeah.
So, in some sense, it wouldn't matter what you disconnect first, you know, in a lot of the case, which is good. But that's my advice as far as that order is concerned. Make sure that the counter electrode is the last one you connect when you're starting, and the first one you disconnect when you're done.
Yeah, I think that's pretty good. I don't have anything to add to that. It's like
It's just a safety thing. It's it's kind of probably a good idea. So it looks like while I was rambling about that, we got a few other questions.
yeah. So I think it's
Shadab.
Shadab. How to make sure the electrode doesn't dissolve in the electrolyte. I've been using 1 molar potassium dichromate for P.PSS electrode, which I forgot what P.PSS electrode
P-dot is it's
an electrolyte.
is it? Yeah.
Is it?
P-dot PSS is poly 3,4-ethylene dioxythiophene polystyrene sulfonate. Why did you know that?
Yeah, I don't know.
I just found the Wikipedia page. That's how I did that.
So that's
Polymer mixture of 2 ionomers. So I guess you're worried that this is going to dissolve in your electrolyte. And you're saying, does this, I guess the question that I have is, does this dissolve independent of potential? Because if it does, I'm not sure there's anything you can do. If the electrode just is soluble, the electrode or the film, this polymer, whatever you're using, is soluble in your electrolyte, it's probably not going to be really tenable to do electrochemistry with this. Like, I mean, right? It's like, how do you keep it there? And maybe that's your question. I guess my answer is I don't think you can. If the answer is that, well, perhaps it's more stable in acid than base, you might have to stick with, right, a more acidic or more basic, however the case may be. There are some materials that are really stable in acid, but if it becomes alkaline, it'll start to dissolve, for example. So those are situations where you can control the pH of your test solution to make sure that your electrode is stable. But if it's fundamentally unstable, independent of the potential you're applying, I don't think you can do anything. I mean, I don't know what you could do unless you were to have some sort of film protecting it, inhibiting its dissolution or something, but then that would inhibit its electrochemistry too. So I think that's the best I can give you for names. I don't know if you're going to put it. I don't know anything specific about P.PSS other than what I just looked at Wikipedia.
Yeah, if your electrode is so how do you know whether it's dissolving or not? Because I just looked it up. It's like potassium dichromate, it's a strong oxidizing agent. Okay, and it may start to oxidize the organics on the P.PSS. So to a certain degree, if you leave 1 molar, over time you'll actually just see, like, is your electrode discolored? Like, if it was oxidizing and stripping parts of it off, your electrode would look discolored visually, even a little bit of it. So that's one thing. And sometimes when you do electrochemistry and you apply voltages, you may remember whatever you do on the working electrode also happens, like the opposite has to happen on the counter electrode.
Yeah.
So you may even see reduced species on the counter, like it almost gets plated on. And so if those reactions are happening, and if you put your electrode in the system at no applied potential, and you start with like a non-zero current, it's kind of like, something is happening. It's probably dissolving or reacting or something like that. So also looking at, like, when you just put it in at OCP, is current flowing in your cell? That's another way to tell if some reaction is happening that might be dissolving your electrode. So those are that's my 2 cents.
That's a good point. Yeah, as far as the measurement thing is concerned, yeah. Is there something happening when you don't think anything should be happening?
Yeah. All right.
It looks like Mari was following up a little. I'm not sure if I completely understand this question. You were talking about the graphene quantum dots. That's what GQD meant. Something about detection of pesticides. Looks like I'm not sure if I understand your question. Electrochemistry field going on nowadays in real-time application. I don't know if you mean in general or with respect to your quantum dots and pesticide detection. If you can clarify, I'm not sure, if you're just asking us what electrochemistry is
going
the
on.
most important or something like that.
Yeah.
for real-time applications, or you're asking about the applications of your materials?
I'm
If you're asking about the application of your materials, I have no idea.
I'm gonna be rude and actually say like there's almost no like quantum dots used in pesticides. Like I don't know if that's a thing right
I
now.
mean, I don't know, maybe it is, I have no idea. I don't know anything. I don't know much about quantum dots and that whole field and those things. I think it's a cool, fascinating thing. My one general question, and probably because I work for industry, is what in the world are you scaling up if it's quantum dot?
Oh well,
Right? I mean, if it's, I mean, maybe you can make a tremendous amount of it, but
yeah.
but this seems like a cool educational topic to investigate some stuff. But I wonder about the scalability of something like this. So maybe I'm being fooled by the name for sure, because maybe you can generate a lot of catalyst material to run some processors. I guess, but if your question is just a general one about what electrochemistry field is important, the answer is batteries. That's just the answer.
Going on
Like what
nowadays.
what electrochemistry field is like the biggest for applications? The answer is batteries.
Yeah.
There's no bigger and more important and more heavily studied field in electrochemistry right now than batteries. They're in everything. Your phone, your cars, your laptops, and as I've said this, I say this from time to time. This question comes up. Technology requirements are improving faster than batteries are, which means that batteries are always trying to catch up, which means there's always an impetus to study batteries.
Yeah.
Because we always are going to continue needing better, more longer lasting, better deliverable, right? All of it, safer, more sustainable batteries in general, because batteries are the answer, right? All of we're trying to more electrify energy sources and everything. That's the goal, and that is achieved, generally speaking, through technological advances, and we get there by making better batteries. So that's really the biggest push in electrochemical research right now. Really, I mean, there's obviously people are studying a lot of other things for sure, but batteries are the big thing. They have been for some time, in my estimation.
Yeah, I think we're part of the Electrochemical Society, International Electrochemical Society. They have divisions. The battery division is like half of the entire Electrochemical Society. Like every other thing, like
I bet you after some
analytical,
time, their powers were going to have doubled.
Soon their powers will have doubled since the last time.
Since the last time I joined the battery division, powers.
It's huge by comparison. So compared to every other thing, like corrosion sensors, I mean, there is the whole solid state aspect, but
well, that's like an offshoot of that. Like, so there are like solid state batteries and things. So I think that there's some relation there.
Oh, I was thinking about like the semiconductor industry uses electrochemistry, but it's outside of my purview of like what I understand about it.
There's definitely some more there that's a little bit
that like I don't understand, but yeah, hopefully that answers your question. Hopefully simple. Okay, I think those are all of the.
got it.
I think we got it. I think those are all of the questions that we got. If you have any more questions, please feel free to type them in. And if you don't, like if we end this relatively soon, you can always type. We usually put up sometime next week the next live stream. You can type your question ahead of time, and we just write it down, and we'll make sure that we answer it, so that you can catch it the next time. And sometimes if we can't answer, sometimes there's some questions that you guys ask that we can't answer, we usually tell you. So I think there's even a guy, he had some questions about like AC cyclic voltammetry and like total harmonic, distortion like that. We actually don't know that much about it. So, so we apologize, but we try to answer.
We answer what we can, and we don't answer what we don't know.
Yeah, but luckily you guys have asked questions that are at least all within the purview of cyclic voltammetry, EIS, most applicable aspects of electrochemistry. So hopefully that's helpful.
Yeah. And next week you're going to be in.
I'll be at the
ACS meeting.
Yes. Next week I'll be at the ACS meeting in San Francisco. So if you are in the San Francisco area, or if you're going to be at the ACS meeting, stop by the Pine Research booth. You'll have a chance to meet me and my other colleague, our other colleague Tim.
Alex is more famous, so make sure when you stop at the booth, you tell Alex how famous he is, and you ignore Tim. That's right.
No.
I'm just kidding.
Oh god, yeah. Some of the people just like, yeah, it's crazy when like, thanks to you guys for watching our YouTube videos and stuff like that. It's like you guys know us, but we don't know you as well. This is our chance to know you.
It's yeah. You'll go in public, and I mean, it's not fame because there's like 12 people around the world who do electrochemistry.
Right.
But when they all know you and you don't know them, sometimes you feel awkward. So
Yeah.
yeah. But we apologize when we mispronounce your name, and we apologize when we don't recognize you in person.
Yes.
But yeah, we do appreciate everybody who joins and comes up to us at booths and tells us that you like our content. We're happy to make this content. We're happy when we get people telling us that it's been useful for you. I mean, that's the idea, of course, right? So
yeah,
if nothing else, we like contributing to the future electrochemists, and everything. So thank you all for joining us this week. We'll be back next Friday for another installation of Ask Us Anything About Electrochemistry. And I hope everybody has a great weekend.
All right.
All right.
See you soon.